So technically what we're talking about here is 1.2, the sequel, right? Part 2, right? We did part 1. Now we're doing part 2 of it, stuff we didn't get finished. And all of it was dealing with graphing equations, right? The graphs of equations. And we talked about plotting points, and we talked about using the intercepts. And today we're talking about symmetry, right? So symmetry, does anyone have a good definition for symmetry? Does anyone kind of know what something is when it is symmetric? Our faces are kind of symmetric, right? If you cut it down the center, it's kind of the same on both sides, right? Same with our bodies, like one arm, one leg on each side. And that's basically what we're saying with symmetry, is something would be the same on both sides. And there's different ways of testing for symmetry. We can test for symmetry graphically, or algebraically. I am going to give you the rules for both algebraically. I think that's right. That is a lot. That is a lot for a word. We are going to focus mainly on algebraically, but I will show you the rules and kind of how it graphically works as well. And we'll start with graphically because that's the least useful one for us. Graphical tests for symmetry. One, I'm going to have to take off my glasses to do this so I can see my cards. A graph is symmetric with respect to what axis are we talking about first? The x-axis. The x-axis. I can't spell today. I can't write today. If, whenever there is a point, or there is a point xy, there is also a point x negative y on the graph. So what it's saying is that if I graph an equation and it's got all of this craziness to it, I can pick any point on that graph, right? So say I have the point 3, 4 on the graph, right? It can't be symmetric with respect to the x-axis. That means on both sides of the x-axis, on top and on the bottom of that x-axis, unless I also have the point 3, negative 4. So what it's saying is for every single point on that graph, it's going to have a point with that same x value and an opposite y value. So if I had a point -2, -3, I would also have to have a point that's -2, +3, right? Because that is the opposite, right? It's saying for every xy, I also have to have a point x minus y, which is just the opposite of this one. Does that make some sense? And we can kind of look at that on a graph. Like if I have, whoops, that was supposed to be a graph. Pretend that's a graph, right? Say I have something that looks like this, and pretend this is a point 1, 1, right? I would also have to have a point 1, -1 on that graph for it to be symmetric with respect to the x-axis, right? Number 2, a graph is symmetric with respect to the y-axis if there is a point xy, there is also a point, in this case, minus x, y. So if you look at what we just wrote right here, right, we were saying with respect to the x-axis, that means on this side of this is our x-axis, right? This is our y-axis. So if something is symmetric to the x-axis, it means on this side, it has to be the same as this side, right? Here we're talking about the y-axis. So we're saying everything that happens on this side has to have an exact match on this side, right? So if I have a point at 1, -1, I also have to have a point at -1, -1. Does that make some sense? And you see this one a lot with quadratics, right? Because quadratic equation is symmetric, right? You would have something like this and something like this. And every point here, like if I had a point here at 1, 1, here I would have a point at -1, 1. Does that make some sense? I got a head nod in there. I'm still getting blank stares from all of you, so I'm hoping you're kind of seeing that. And it'll probably make way more sense when we test for it algebraically or not. I don't know. The last thing that we can be symmetric about, or symmetric with respect to, we could say that a graph is symmetric about the origin, with respect to the origin. Does anyone know what the origin is? Yes, Moses got it. That point 0, 0 is the origin. That center point in our graph is the origin. If there is a point xy, there is also, oh, that's terrible handwriting. There is also, can anyone guess what this point might be? One, we negated the y. The other, we negated the x. What do you suppose is going to happen with this one? Any guesses? So if there is a point xy, there is also a negative x, negative y. They would both be opposite, right? So what does that mean? That means if I have a point 3, 4, I also have to have a point -3, -4. If I have a point -2, 1, I also have to have a point 2, -1. Right? Because basically we're saying that it flips on the x-axis and the y-axis. You see that a lot with cubes, the graph of a cube. You'll see, looks like, I'm not going to be able to draw this very well, but it looks kind of like that. And that would be something with respect to the origin, right? I would have a point here that's 1, 1, but I would also have a point here that's -1, -1. Does that make some sense? So we flipped, right? It's not, if you look here, it's whatever's happening here has now been flipped over here, and then whatever was happening here is now flipped over here, right? It flipped on both sides. Next, we're going to talk about finding symmetry algebraically. The algebraic test for symmetry. I prefer it algebraically. I like being able to see it graphically, but it makes so much sense for me, much more sense for me to be able to determine it algebraically. It doesn't help me to algebraically testing for symmetry. I should have just left it at algebraic and saved myself. I am going to go ahead and just write the rules on this and then give you examples of finding all of them instead of giving you examples with every rule on this one, because it's a little easier to do when we're talking about algebra. So number 1, again, the graph of an equation is symmetric with respect to the x-axis when replacing y with negative y yields an equivalent equation. Boy, my handwriting is looking terrible. I apologize for that. Yields an equivalent equation. That's saying that if I take whatever my original y value is and I replace equivalent equation. If I take whatever y value I have and I replace it with negative y, and I wind up with the same problem once I solve it through, then it is symmetric about the x-axis. Number 2 is going to be the same thing, right? Only we're talking about the graph of an equation is symmetric with respect to the y-axis if when replacing, so this time we're going to replace x with negative x, right? If when replacing x with negative x, it yields an equivalent man, that's terrible. It spells equivalent equation. And I'm going to show you examples of all this. Right now it's just getting the little rules down. Last but not least, what do you suppose that I am replacing? First time I replaced y with negative y. The next one I replace x with negative x. And this one, we're going to replace both of them, right? We'll replace x and y with negative x and negative y for the origin, right? I just want to kind of go ditto on all of this and not have to write it again. Is symmetric with respect. Doesn't feel very respectful right now. To the origin if when replacing that's okay, Anthony, everything's being recorded. If when replacing x with negative x and y with negative y, it yields, the good news is this is the last bit that's wordy for me, an equivalent equation. So those are our rules. Let's see what they look like. All right, let's see what they look like in practicality. So if we're going to test for symmetry algebraically, and we are asked, it'll probably be worded like test, and it'll give you an equation y equals 2x cubed for symmetry. And it'll say with respect to both axes, with respect to both axes, right? AX, ES, which is like axes, and the origin. All right, so we want to prove it for all of them. And we're going to do one at a time. We're going to go, okay, well, we've got our original equation, right? Y equals 2x cubed. For the x-axis, to test for the x-axis, we're going to go, okay, well, we've got y equals 2x cubed. And they're saying, right, if you look up here, what do we replace to just for the x-axis? We're going to replace y with negative y and see if we get an equivalent equation, right? So we're saying that this would have to be the same as this. And in this case, it's not, right? Y equals 2x cubed is not the same as negative y equals 2x cubed, right? So we're going to say that there is no symmetry about the x-axis, right? It's not equivalent. So it is not symmetric, right? Not symmetric. Symmetric. for x. Next, we have to test the y-axis. Now, the y-axis says that if we replace x with negative x, it should be equivalent, right? So if I have y equals 2x cubed, and I replace the x with negative x, I would have y equals 2 times negative x cubed. Now think about negative x cubed. That would still come out negative, would it not? Right? If I had negative x times negative x times negative x, right, I would have negative x cubed, right? At the end. So I would be able to say that y equals minus 2x cubed, right? That is not the same as y equals 2 times x cubed, right? Is it the same? Right? Because that's the question we're asking. We're asking, is this the same as this when we're done? And in this one, no, it's not, right? Not equivalent. Not equivalent, so not symmetric. Equivalent, so not symmetric. Last thing we have to check is the origin. We have y equals 2x cubed. If I replace that with negative y equals 2 times negative x cubed, I am going to wind up with negative y equals negative 2x cubed. If I have a negative on both sides, can I get rid of it? If I just multiply or divide both sides by negative 1, doesn't that go away? Do you guys remember that? Because we don't care what negative y equals, we care what y equals, right? So all I have to do to find out what y equals is divide this by negative 1 and this by negative 1, and I wind up with y equals 2x cubed. And that is what we started with, is it not? So it may not be equivalent on the x, and it might not be, it might not be symmetric for x, and it might not be symmetric for y, but this is symmetric with respect to the origin. And you can shorten that. You can just go sim to origin, right? Save yourself some letters. Is it a pain? Yeah, it's kind of a pain. But you have to do this. You're going to be given equations, and you're going to have to determine whether or not it's symmetric with the x-axis, with the y-axis, and with the origin. The good news is I only gave you a couple problems like that. I focused the rest on writing circles. So that is what we're going to talk about right now, writing the equation of circles. We're going to make a quick jump, unless somebody has questions before I jump. But ultimately what you're going to be given is you're going to be given an equation, and you are going to have to determine when you replace the each one whether or not it's equivalent. And you might have to watch that example a couple times, but the good news is it's recorded, and you'll be able to go back over it and over it. It depends on the circumstances. It depends on the problem. I would have to see a problem with that to know if that's what we would need to do. I'll look for one though before I leave today in the book and see if there is one. And if there is, I'll just make an example problem. I'll do a little video of an example and post it to PowerSchool for you. Now, since your book jumped straight to circles, that's what we're going to do too. When we're talking about circles, all we're talking about in regards to circles today is the equation of circles. Ultimately, a circle is any set of points x, y, right? Well, on a plane, right? Like a Cartesian coordinate plane, which is the kind we've been using, that are the same distance from another point, right? That we're going to call HK, or the center. And to find that distance, same distance, the distance that we find between them is what we call R, or the radius, right? So they're saying that I have this one point, right? And they're saying that same distance away from that point is what a circle is, right? It's all those points that are the same distance away. Now, I don't know if these are the same distance away or not, I'm guessing. But all of those points, when we draw a line, right, will create a circle. Every point on a graph that's the same distance away from the center point is what makes a circle, right? And the way that we find those is using the distance formula. The way we've come up with the equation of the formula is I have a point right here. This is my HK, and this is some other point, XY, that's on the circle. And we learned the other day, right? Pythagorean taught us that we can find the distance between any 2 points on a graph, right? By using the Pythagorean theorem, and we came up with that distance formula of D equals, you remember this? x2 minus x1 squared plus y2 minus y1 squared. Do you remember that? Anybody remember that? We just did it the other day. Kylie remembers. The distance formula, right? Well, the distance formula, I'm going to write it prettier over here so you can see. It's also saying that the radius, because we know that this distance right here is our radius, right? So it's also saying that the radius equals x2 minus x1, or what we would call what? x2 minus h. Let me write that prettier. We don't even need a 2, right? If I look at this, what do I have? I have my 2 points, right? I have my center, that's HK, and I have my other point that's XY, right? So I know that I could go x minus h squared plus y minus k squared, right? Using those 2 points. Does that make sense? If I'm using the distance formula? The way I come up with the equation for a circle is if I square both sides of this equation, right? If I square this and I square this, This becomes the radius squared. And this whole piece right here goes away. This just becomes x minus h squared plus y minus k squared. This is the standard equation of a circle. I am not going to ask you to get here, but you're going to have to play with that a little bit, because on a lot of these, you're going to be given 2 points, and they're going to say, hey, write the equation of a circle given these 2 points, a center, right, which is your HK, and then another point. And you're going to have to come up with this equation. How are you going to do that? Well, I'm going to show you. So if you were told to write the equation, and you will be multiple times, of a circle, with a point (3, 4) and a center (-1, 2). So you have your 2 points, right? What don't you have is what you don't have is your r. You don't have your radius, right? But we know this is a point, so this is just our xy, right? This is a point too, it's our center, so we'll call it hk. What we don't know is the radius, but the way to find that radius is to use the distance formula. So we know that the radius is going to equal x minus h, so 3 minus minus 1, 3 minus minus 1 squared, plus 4 minus 2 squared. And if we play with this a little bit, right, we're going to get 3 minus minus 1 is the same as saying 3 plus 1, right? 4 squared is just 16. Here I have 4 minus 2. Well, that's 2. When I square it, that's going to be 4. So 16 plus 4 is 20, so I have the square root of 20. That is my radius. Right now, we can go r equals the square root of 20. Now we just have to plug it in to this formula. What do I know? I know that r squared, right? R squared, well, for us, r is square root of 20. So we're saying the square root of 20 squared equals x minus h. What's our x? We don't even care, right? Because we're using it for any point. Our h, though, is -1. So we're talking minus 1. So it'd be plus 1 squared equals, plus y minus whatever our y center is, our k, squared. What is the square root? What is the square of the square root of 20? If I have something in a square root and I square it, what do I get? Anyone remember this? That's like saying the square root of 20 times the square root of 20. And it just gives me 20. Anytime you square a square root, you're left with just what's under it. So if I have the square root of x and I square it, I wind up with x. Yeah, when you square something in a square root, it's just whatever is underneath there. And so if I have the square root of 20 here, squaring the square root of 20, I wind up with 20 equals x plus 1 squared plus y minus 2 squared. And what's awesome about this is with this information, I can graph a circle if I want, right? Because I know I have a center point. My center point is 1, -2. And every single point around it is going to be exactly 20 units away from that point, right? So if I have a point, say it's 1, -2 is my point, right? I know 20 units away here, I'm going to have a point. 20 units away here, I'm going to have a point. 20 units away here, right? Because that's what a circle is, right? Once we know the radius, I can make anything that long away from it, right? And they'd all connect because every point on a circle is exactly that far away from the center. Now, I don't know how clear that was, but we can do that with anything, right? I can go, okay, I have a center, let's say a center of 3, 4. I am just making this up, right? And I have, we'll call this my H, and this my K, right? We're saying it's the center. I know that there is a point at, let's say 2, 6, right? I can find the distance between these, and I can write the equation of a circle, right? Because all I have to do to find the radius, that distance between them, is to go ahead and play with this, right? I'd go 2 minus 3 squared. Always remember that we're doing our x minus our h, right? Our y minus our k, plus 6 minus 4 squared. And that's going to give us 2 minus 3 is -1, but when I square it, it's just 1. 6 minus 4 is 2. When I square it, it's 4. So I have the square root of 5. That's my radius, right? And so now I can just plug it in. I can go the square root of 5 squared equals x minus whatever my h is. So x minus 3 squared plus y minus k, which is 4 squared. When I square that square root of 5, I wind up with 5 equals x minus 3 squared plus y minus 4 squared. So you'll have a couple, I think there's like 5 of those problems I gave you guys. Everything is already posted in PowerSchool. Well, you have, I think there's like 5 of this kind, and then there's 7 of the other? There's not that many, are there? I did 5 of the first kind, 33, 34, 35, 36, and 37, and then numbers 67 through 71 of this kind. So it's like 5 of each.
There's like 7.
5 and 4. There's 9 problems.
Maybe that was kind of slow.
Yeah. So it is all posted in PowerSchool. It's page 20 in the book. If you're using the PDF, it would be the same PDF that we used the last time. I am sorry for